Good day again, everyone. My name is Adam Harris, Managing Director from here at C-Therm Technologies. Very pleased to welcome you to our webinar presentation today titled Quantifying Thermal Touch Performance, Thermal Effusivity Applied in Fabric Selection, Validation, and Quality Control. Online with me today, I've got my colleague Arya Hakimian. Arya, I'll get you to just wave hello. Arya is one of our application specialists and is going to be detailing some of the work we've been doing here at C-Therm Technologies in support of a special project with researchers at the University of Oregon. And we're very pleased to have with us Dr. Susan Sokowolski, who's director of the Sport Textile Center there at the University of Oregon and has been leading this study sponsored with major leading brands in the athletic apparel industry. Susan's a former researcher from Nike, has incredible depth of expertise when it comes to technical performance of textiles and apparel, and brings a design aspect as well in her background. So today's format, the webinar should run for approximately 1 hour. We're going to take you through some background material on who C-Therm Technologies is, what is effusivity, how do you measure it, and what are some of the applications where it could be of interest. And then we're going to pivot really to an update on this special project that we've been partnering with the University of Oregon on. So throughout the presentation, if you have any questions or comments, if there's any aspect that you would like us to delve into deeper, please feel free to use the chat box. If we don't address the comments in real time, we do make a point of reviewing them at the end in the Q&A session. So I just wanted to encourage the use of that utility. Yes, so I've mentioned Dr. Sokowolski, Associate Professor and Director of the Sports Product Design Program at the University of Oregon. Really pleased to have Susan online with us, and we'll be sharing some of the content from the project that she's running. So we'll segue into that portion about halfway through the presentation, and I'm sure you're all excited to learn on some of the work that she's leading on developing thermal spectrums and really addressing the question that we're faced in testing the effusivity of materials is, how can we say when we can call a material warm feel or cool touch? How can we classify that performance? What does that look like? And what body of work supports that claim? So all those answers will be addressed, and we'll talk about how we're working on that challenge with Dr. Sokowolski's presentation. A little bit of background on C-Therm Technologies. Our reason for being, our raison d'etre, is really about simplifying thermal conductivity and related transient, heat transfer properties of materials. So a lot of the work we do is in thermal conductivity, but you look at, when you measure thermal conductivity, there's other heat transfer properties of materials that are very interrelated. And thermal effusivity is one of those thermal properties that is very much tied to thermal conductivity. Just like thermal diffusivity, other aspects, the heat capacity of the material. This is really the world that C-Therm lives in. We're experts in characterizing those thermal properties. And we've really developed a very specialized niche in the world in characterizing conductivity and effusivity in particular. So we're not a broad-based lab instrument company. We do one thing and we do it really well, which is measuring those thermal properties. And our goal is to advance it in terms of simplifying it, making it easier, more accessible to measure, and also possible to measure in more challenging environments. In textiles, that means in thermal chambers and high humidity environments, humidity chambers, etc. And that's really what we're about as an organization. Now, I've included this slide in the last few presentations because I think it would be a mistake to assume that the world is business as usual. We certainly recognize what's happening in the world with the COVID-19 challenges and understand this is probably impacting you all a great deal as it is us also. But I like to take these opportunities where we have a significant group of stakeholders online with us just to pause and ask a couple of questions about how this is impacting your business, your operations, your research. And I'd encourage you to use the chat box and just share with us a little bit of a sense of what your world looks like right now. Do you have access to your facility? You know, are there, are you facing, major adjustments in your business? Is there any way that we can help mitigate some of these challenges? One of the ways we've been helping some clients is we still have access to our lab facility. We're a reduced capacity. We don't have as many people working. We're implementing all of the social distancing advice that we're receiving, but our facility is still accessible. And so we've helped a number of organizations continue to advance their material characterization needs through contract testing. If that's of any way we can be of help, please let us know in the chat box, and we'd be certainly happy to help you with this. But the other part is this is a bit of a quick survey and getting a sense from you of how long do you see these restrictions in place for you and your business? And are there any long-term changes you see to your industry as a result? A shift in business focus, longer-term downturn in the industry which you're working. These aspects are very interesting to us and help us adapt and address and hopefully better support you as a partner and client and stakeholder. Okay, that's it. I wanted to give a quick overview of our product lineup, and the product on the far right is going to be heavily featured in today's presentation. It's the TX Touch Experience platform. It operates an MTPS, Modified Transient Plane Source sensor. And this is what was used in all of the characterization work that Arya has done in support of Susan's project. And we'll be presenting those results shortly. In the middle, we have another research grade instrument called Trident. And Trident is for a wider range of industry. So the TX system is really meant for textiles and consumer goods where there's an aspect of wanting to understand the touch property and quantify that performance. The Trident system brings multiple different methods together and is really appropriate for broad-based research applications. Could be polymers, ceramics, metals, paste, liquids, powders, and being able to measure primarily thermal conductivity, but other properties such as diffusivity and effusivity as well. On the far left of the screen is what we call the TC, or thermal conductivity kit. It's a very low cost offering. It's really oriented towards more of an academic audience where the researcher may be dealing with a reduced budget. We've seen interest from groups wanting to set up some home capability while you're removed from your lab for a prolonged period of time. This gives you the ability to measure conductivity of solids up to about 65 watts per meter Kelvin. It really only does solids and higher viscosity pastes. It can also work for powders. So it's actually a very capable kit at a very low cost. It's not the same accuracy and sensitivity as Trident. Trident is really more of a research grade product, but the kit is a great offering. You can get one of those configured. You put it together with a Keithley source measure unit and laptop, and you can generally do that for about 11,000. So it's a great offering, particularly if you're of very limited budget. But really, we're going to be zeroing in more on the TX Touch Experience system. This offers the capability to test from -50 to 200 degrees C. It's very easy to use. There's no user calibration required. It's factory calibrated. It's a plug and play format. Very sensitive instrument. Accuracy better than 5%. Precision better than 1%. And I'll just reiterate the offering on just before we started the formal presentation. Just behind Arya, you actually will see over his shoulder there, the TX system there on the back. The Trident sitting on the table, but the TX system is just behind him. And anyone that would be interested in scheduling a private demo of this, please enter in the chat box, and we'd be happy to schedule that with you. That's a great offering. We can do those in 15 minutes, a really quick review of how it works operationally. This is a little bit closer view of the sensor. I've got some other pictures here that relate to that coming up. This is a quick quote from one of our clients at Adidas, from Christian Haid, Dr. Christian Haid, who's in apparel intelligence. Just comments very succinctly, the device is working perfectly. So we take that as a great compliment and point of pride. We've got dozens and dozens of client testimonials on the website if you'd like to see others. Jordan, if you're moderating the session, I'll just ask you to maybe plug in that link to the chat box when you get a chance, if anyone wants to check out some of the other client experiences with our technology. This is what the sensor looks like. It's MTPS. It's quite a mouthful in its long form. That's modified transient plane source. We just call it MTPS for short. And I'll be describing how that works in the next few slides. But what does it measure? It measures two thermal properties. Outside of textiles, what it's primarily used for is measuring conductivity. So that's where you can apply it in all kinds of different scenarios, from ceramics, polymers, metals, liquids. It is a liquid-proof sensor, so it can test liquids very easily. And really has broad application. And we have a host of other webinars that have been recorded on explaining how the MTPS sensor is applied in those other scenarios. But today is all about textiles. And the main thermal property we're interested here from the textile perspective is called thermal effusivity. Now, if effusivity is a newer term to you, first off, it's not emissivity, which is an optical property of a material and is not related at all. Thermal effusivity, sometimes called thermal inertia, is described as a material's ability to exchange heat with its surroundings or with other samples in contact with it. So it is the thermophysical property that determines the touch attribute or the touch sensation in coming in contact with it. It's defined as the square root of the thermal conductivity, density, and heat capacity. But it's important to note we don't measure those things individually and then calculate effusivity. We're measuring effusivity as a bulk quality of the material or characteristic of the material. So it's sometimes called thermal inertia, and it really is that thermal property that defines whether something feels warm or cool to the touch. The easiest way to relate to this in your office is to touch the top of your desk, the wood table, and then move your hand over to the metal filing cabinet or the base of your chair. And the first thing you notice in terms of differences between those materials is that, in all likelihood, you're sensing that the wood feels a bit warmer and that the metal feels cooler to the touch. Well, if you just stop and think about that for a second, everything in your room is the same ambient conditions. Everything should be the same isothermal temperature. But what's different there is your hand is a heat source, and it's the effusivity property of those different materials you're coming in contact with that is defining the interfacial temperature when those two different bodies at different effusivities meet. So it's the effusivity that will determine the interfacial contact temperature. And so it is the thermal property that matters most when we're trying to understand the characteristics of touch. And there's a broad base of application for this, but most of it relates to applications in textile and related goods. It does also give us the ability to derive other thermal property data. If we understand both conductivity and effusivity, we can, for example, input a density value in this equation and then see how CP would pop out. So it does give you a direct path to heat capacity as well, if that's of interest, although I would caution you, it's not as accurate as a DSC. There are more accurate ways of determining heat capacity. So how does the sensor work? There are two circuits primarily to the sensor design. One is a coil that you see in the middle of the circle there with the big red arrow coming out of it. And then there's a second circuit that goes around it, which is called the guard ring. And this is a patented innovation by C-Therm Technologies. It's a really important distinction that coil is surrounded by a heated guard ring. Both of those circuits are electrically heated. And we do that to ensure that the heat path from the coil has a one-directional pathway into the sample that's in contact with the sensor. So the way the measurement works is we're applying electricity to those circuits. That provides an electrical heating. And at the same time, we're monitoring the voltage drop on the coil as it's calibrated to temperature change. So we just use the voltage drop as a proxy or calibrated temperature measurement. So fundamentally, you can just think of this as a measurement of temperature rise over time. And it's the slope of that temperature rise over time that's inversely proportional to the thermal conductivity. So if I have a very flat slope in terms of the temperature change over time, it means I have a really high thermal effusivity material, something that is going to feel really cool to the touch. Conversely, if my slope is really steep, it's an inverse relationship. So it means that my material is going to have a really low thermal effusivity, and that's going to have a really cozy feeling to it. Now, this is the theory of how it works, and we can give you some papers that detail this in much greater detail. And Jordan, I'm going to keep asking for your help as we go through this. The method selection guide here, if you want to insert the link to the method selection guide, that's a great resource in looking more at the theory of operation to this. I will note, though, there's no regression analysis required in running this measurement. I spoke at the beginning that this is a really simple, easy measurement to administer. We've had high school students come in, get a demo, and actually take measurements with a very high degree of accuracy with 10 minutes training. So it's really meant to simplify life in terms of measuring these thermal properties. So what you get in terms of the software output is a tabular output of the thermal conductivity and effusivity results. And it's plotted like what you see on this screen capture with the tabular output of those thermal properties and also the temperature recorded along with some diagnostic data that speaks to the quality of the measurement. This application in textiles, the journey we are on here, started about, I would guess, 7 to 8 years ago. And it started with a really great researcher from Marks. Marks is a Canadian retailer of sportswear, a lot of textiles and garments that are used in the outdoors. So anyone, you think of thermal underwear as a primary example. And Shannon Yanni approached us about 7 years ago on this aspect of wanting to quantify the performance in the fabric selection for some of that thermal underwear. And Shannon, to her credit, really took this idea and ran with it and was successful in establishing an international ASTM standard based on this method. So that was established, I think, in 2016, so about 4 years ago. And since then, we've seen a lot more adoption in terms of applying this method to quantify that touch property of whether how can you rank and really quantify the performance in terms of coziness. And that was the question that we were originally faced with. So I'll talk a little bit more about Marks. This was an effort that we're very grateful to. I see we've got a number of Shannon's colleagues on the line with us. I think Miles is with us. Hello, Miles. But I really want to give credit to Marks in leading this effort several years ago. I think it's been really good for everyone involved in really defining better the requirements for quantifying performance. And I think back to those early days when we started about 7-8 years ago, and it all started with long underwear. So the question being how, we got different candidate materials for the long underwear. Marks has their own private label T-Max thermal underwear. You've got a nice picture here of what that looks like. And so we were able to assist with some of the performance characterization there. And there's a really good webinar that we recorded with Shannon a couple of years ago. And if anyone's interested, we can certainly provide you the link to this. But this is a summary of some of that work that was presented. Just giving the effusivity values on the far right column for different fabrics. And these are fairly dramatic examples for illustrative purposes. There were some much more nuanced cases that we looked at as well, but this just illustrates the value of effusivity and really quantifying that sense of coziness for fabric selection. So with effusivity, the lower the value, the warmer the material is going to feel, the cozier it's going to feel. The higher the value, the cooler it's going to feel to the touch. So if you're choosing a fabric based on coziness, certainly out of the ones presented here, the polyester thermal fleece, polyester interlock, polyester air mesh, and the nylon poly jersey knit blend, you would certainly be leaning towards the effusivity based on the criteria for coziness. Now, nobody is saying that that is the only criteria in fabric selection. It depends on the application and intended use. There are certainly a number of other characteristics of the material that would define performance. But if the warm feel or cool touch is part of that, is a critical performance attribute for the product or apparel, then this is where how you can use effusivity to guide some of that fabric selection. Some other user cases. One case is comes from automotive interiors. So in automobiles, particularly as you go up into the higher performance categories, you typically will see more and more finishes on the interior of the vehicle, and often from an aesthetic perspective, we are wanting to see natural materials applied. So leather and wood paneling are two common finishes that you see in higher end vehicles as you go up. But the problem, of course, is that with wood and leather as natural products, they have consistency issues. So you have a higher manufacturing cost to working with them. They're also heavier. So they have a negative weight ratio from a fuel economy perspective. So we would prefer to use and incorporate composites here, synthetics that perhaps maybe look like the real thing, but are lighter, more durable, more consistent, and cheaper. But the problem comes when you get into test drive this vehicle, and if you start, gripping the steering wheel, playing with the knobs on the dashboard, and feeling the paneling, and it feels like plastic, just pause for a second and start to think about what your perception of quality is on this vehicle as you're test driving it. Most people would respond, well, I think it's starting to feel a little bit cheap, or cheaper than maybe some of the other products you're testing in that category. So it's the point we're making here is it's important not only what things look like, it's also important what they feel like. This impacts consumer purchasing decisions in a very real and meaningful way, even if the consumer is not thinking through those individual aspects of, it feels like plastic. Often this can be a subconscious aspect to our purchasing decisions, but no less impactful in the ultimate result. Another example is in baby diapers, so a bit more relatable to the textile space. But diapers is a very big industry, and the performance, the feel, the comfort of diapers is, of course, a critical performance attribute to these products, particularly as they are wetted. So looking at the effusivity of such materials is very helpful in being able to quantify that performance. There's a patent that's been published by P&G also profiling some of the consumer packaging. There's one that describes a baby wipes container having a good thermal effusivity. I think that's the title of the patent. The P&G, I think, has done some really interesting work in this field. I would just caution that effusivity itself is neither good nor bad. It's an indexation of the performance. In some applications, you would want a high effusivity. In other applications, you would want a lower effusivity. But it's being able to quantify that performance and understand how changes in the composition in different chemical treatments, different coatings can alter that performance over other candidates. Okay, the last example I'm going to highlight comes from another webinar we highlighted with a company called Arctic, and they work on phase change material technology for fabric cooling. So they apply a finishing to the material, a coating, to help improve the cooling aspect of the material. And this primarily is applied for the bedding industry. So this is just a short slide that details a little bit of that. If you'd like to sit in on the full webinar with the researcher from Arctic, we do have that in our archived recordings, and that is available for playback if you're interested in a deeper dive. Now, I'll also note that I'm not going to get into much detail on phase change materials in this presentation, but we do a lot of work with phase change materials. PCMs are very interesting as a way of storing heat energy, of heating and cooling selectively. There's a lot of work done to try to enhance the thermal conductivity performance of the material. We just did a great webinar last week on PCMs with Aria's colleague, Sarah Ackerman, and a lot of work done with different additives to try to increase that thermal conductivity. So if you're interested in that aspect, we do have some other content available, but this just highlights the improved cool touch of the material, testing a non-woven high loft sample from Arctic. So the untreated sample came in with an effusivity of around 75, which is actually quite a warm feel, as you'll start to be able to relate to as we present some of the further results. But with that applied coating, there was a significant enhancement, almost doubling the effective feeling of coolness of the material, increasing it to over 125 units of effusivity. Another quick example shows a tubular FR sock material, untreated, around 120, and was able to increase that to about 160 with the treatment. So I know Wim, the president of the group, was quite excited about this because, of course, he can show the fabrics and take them into his clients and get them to feel this in person. But it's another thing to be able to quantify it scientifically, to provide hard data in terms of performance improvement, and really help justify the premium for that product. When you're talking about high performance apparel, being able to command the higher margin, really important to be able to validate some of those claims. And that's one of the common application uses for this technology, is to really back up different marketing claims, different performance claims, as well as aid in the fabric selection itself. The third kind of area or utility is in helping with quality control as well. And at the end of the slide, I'll talk about some of the different third-party test labs that can also assist you in this aspect of running the tests if it's something you're looking to outsource. Okay, I'm going to pass this over to Aria, but one last slide before I do that. This just gives you a bit of orientation on the effusivity properties of different materials. So let's start with a question of what would have an effusivity of 0? This will be a little quiz. You can answer in the chat box if you have any guesses of what would have an effusivity of 0. I'll come back to that in a second. The high end of this index is listed as 1600. And we've chosen 1600 because that is the effusivity, as you see marked on the index of water. And from a textile application perspective, that kind of represents, from what we've seen, the high end of what you would be experiencing. There are absolutely materials with much, much higher effusivity properties than water. Most metals, for example, get into several orders of magnitude higher effusivities, but they're not really applicable to textiles or the space we're dealing with. All right, I've got some answers streaming in. So George and Jose got it right. The correct answer is vacuum. The only thing that really has an effusivity of 0 is vacuum. Air itself has an effusivity between about 6 and 12 units of effusivity, and then it kind of goes up from there. Most of the textiles we work with are between 50 to 400 units of effusivity. You can see that leather comes in at around 400 units of effusivity. Most fleeces are in that 50 to 80 units of effusivity, and this just gives you a bit of a sense of the range of materials in relating to them. So the lower the value, the warmer it's going to feel. The higher the value, the cooler it's going to feel. But the big question that we're still getting and we're looking for help with, and that's really how this all started with Susan's group, is we often get the question from major brands, suppliers to the industry, product developers of when can I call my material cool touch? And when can I call it warm feel? So it's that segmentation of the performance that we're trying to address. And we don't think it's right for us to just declare that it is X value. We really wanted to develop this through consensus and supported by third-party research and evidence that would support that. And the intention is to later take this back to the ASTM committee and formalize this more within the D7984 as an update to that standard. But I'm very grateful for a number of the leading brands that have aided with this project. I'm not going to name them here, but it's a very impressive group of brands and groups in apparel that have really embraced effusivity and are helping sponsor this project with Susan's group at the University of Oregon. And this is the question that we're trying to address with that is when can I call my material cool touch and when can I call it warm feel? We've got a great index already here, but how do we segment that index and give better definition and categorization to that performance? So with that said, I'm going to hand this over to Arya, and he's going to take us through some of the effusivity testing that's been done. And then we'll get to the star of our show with Susan providing an overall update on the project. Okay, Arya, I've stopped sharing, so you should be able to launch your slides.
Alrighty. Hey, everybody. So as Adam mentioned, I'm going to just touch on a few slides here, highlighting a few more examples of exactly what we're dealing with thermal effusivity, but also looking at some of the factors in a little more detail that will influence your measurement result. And then after I wrap up, we'll get to hear from Susan on some of those results that we've been able to get. So at the beginning of the webinar, there was a short video, if you were here a little early, which kind of touched on this. But you know, essentially what we're looking at here is really taking what we have naturally in our bodies, our receptors, being able to help distinguish various properties, whether you're looking if something's you know, sharp or soft, you know, smooth. We have various receptors that can help detail these aspects, but for us, we're really looking at the thermoreceptors, which help relay information about warm and cold or hot and cold there. Now, We have already seen in the past that, our MTPS measurements of thermal effusivity have been shown to positively correlate with your scale of perceived, coolness here, as you can see from this graph. So again, for this study, we're not really, we already know that there is a correlation. So as you can see, as Adam had mentioned, if you do a kind of a test around your office, if you touch something that's made of wood versus something that's made of metal, you generally will be able to distinguish those two from one feeling cooler than the other. And that will correlate to the overall thermal effusivity of those materials. But to Adam's point, again, we're really looking to not necessarily dive into this more so, but really being able to segment where those cutoffs are between warm feel and cool touch. So when we're looking at thermal effusivity measurements of textiles, there's a few things that can influence your results, and they kind of fall into two categories. So whether you're looking at the material side of things, that could be the type of fabric that's being used, whether it's from a natural resource such as naturally occurring cotton, or if it's a synthetic that's being developed in a lab. The different materials can come into influence the effusivity measurements, but also even if you're looking at the same material, that's factors such as your yarn or your thread size, how it's being woven together, and if there's any coatings on it, these can all really influence the overall measurement. And a lot of these come back to relations to the material's density and how much material you have in a given space, or that's going to be actually measured during the testing of that sample. Now, I won't dive into that too much because there's a few slides that Susan will be discussing that kind of touch on that. I really wanted to focus a little bit more on the environmental side, or those types of variables such as your temperature and humidity. Those are two very important factors that need to be understood and also controlled during your testing, really to help give you reproducible and accurate results that you can use to compare to other studies, and not just have one-off. So being able to control your temperature and humidity are very important, and I'll detail a little bit of that related to the ASTM standard. So as we've discussed, ASTM D7984, this is the standard method used to establish thermal effusivity of fabric materials. Now, in the standard, it will give you guidance on how to set up your the test, the sample requirements, various. It gives you all the details, but I just wanted to again highlight the environmental requirements. So the standard states your temperature for your test environment needs to be 21 plus or minus 2 degrees Celsius, and then a relative humidity of 65 plus or minus 5%. And you want to really take those windows and making sure that when you are testing, if you're testing if it's a thermally controlled environment, or whether you just have a kind of a rudimentary setup, that you're monitoring both the temperature and humidity, and you're reporting that along with your results, so you can compare and better understand the measurements that you're getting. So I'm going to talk a little bit about what we did from our side of things in support of this project with the University of Oregon. First off, we received various samples, about 37 samples total for testing, that are being narrowed down for further steps. But we were testing both the front side, or the face of the fabric, and also the back. Now, you might ask why that would be, and really it comes down to a few things, but ultimately, just because you have a fabric or a sample, one side, depending on the finish, or if there's been any surface modification or anything like that, you can experience differences between front and back side, and that can be very useful to understand, especially if you're looking at a product standpoint, whether it's the material that's in contact with your skin while you're wearing it. It may also be the material that will be on the outside. Therefore, if you are doing, walking around a store, you may be just touching a material, not necessarily putting it on. So really being able to assess both sides of the fabric can be very, very useful. And ultimately, what we did once these results were finished up and sent off, next steps, again, they will be used to establish a touch panel study, which Susan will be discussing shortly. So from the sample preparation side of things, this is kind of just an example of one of the materials that was tested. They were sent pre-cut and labeled to us, ready to go for testing. So that was all great. We were able to load in the samples and test them. But one thing to note is, depending on the material thickness, you may require layering of a sample to achieve the required testing thickness. And what is that required thickness? Well, it is outlined in the ASTM standard, but ultimately what you need to do when you're testing any textile material is make sure that your total specimen or your total sample thickness will be greater than approximately about 1 millimeter. And what that facilitates is the heat pulse during the measurement that's delivered from your MTPS sensor will not penetrate through the sample itself and reach the other side. So your heat pulse or your measurement is maintained within your sample. So it's, again, that's one factor that you do have to monitor and make sure you're following the, again, ASTM guidance for setting up the measurement itself. And each set of samples were preconditioned prior to testing. So just to touch on that a little bit, just because you have your room or your test area conditioned to your 65% humidity and 21 degrees, if you're bringing in a fabric that's been in another room or maybe sealed up in a box, and you just put that in the room and you start testing it, there is a certain amount of equilibrium or equilibration time that's required for that material to actually reach your test conditions. So you actually want to precondition your samples to those temperature and humidity requirements prior to running your measurements to make sure that they will not be significantly changing temperature or absorbing moisture over the course of your analysis. And lastly, just kind of touching on the actual test setup and the condition. So this.
No problem. Thanks, guys, for that great introduction. So I'm going to take you through the perception side of the research that we're doing. And we have this slide here, which we call our project fact sheet. So I'll go through this first to kind of give you, just a little perspective on like what we're addressing in this study and how we're moving along with the calendar. So our project objective is to measure thermal effusivity and human thermal perception in dry conditions of key sport apparel materials. And this project, like Adam mentioned, will ultimately address the question, can we label materials warm or cool touch? We'll do this once we've collected the data through statistical analysis, and we'll use that analysis to determine similarities and variances between data. What our goal is to update that spectrum that Adam showed you with sports apparel materials and really see like what that spectrum looks like from warm to cool touch. And we're hoping that those spectrums will be devised to establish thresholds. Oh, looks like we lost my presentation. Let me pull that back up, guys. So we use that information to devise thresholds for performance characterization of tested materials. And our end goal is to share that knowledge at industry conferences and academic journals. Adam's already described what thermal effusivity is, and we're going to measure it per the method Aria just went through, and they've already measured those materials. I think what's important here to highlight is that we evaluated 37 samples. Those were provided by industry partners, and each of those 37 samples, the face and the back, we collected metrics from. For this study, we are defining human perception as the process of perceiving something with the senses. And we will measure the sense of warm or cool touch from 15 of the 37 materials evaluated for the project. How we'll measure it, I saw that question come up on the chat quite a few times. For this study, human warm or cool touch perception will be collected with a fingertip test for 15 materials for the face and back. And the materials will be ranked from warmest to coolest. The calendar here is a little cut off, but you can see we started this project back in the summer of 2019. We developed an IRB, and I spent quite a while with the industry partners that are on this project, really helping to pick materials and also to develop the human perception test protocol. What was interesting with this study is that you can imagine all the companies that we worked with had their own method of perception testing. So we had to come together to create something that everybody agreed with and really answered all the questions we were looking to get after. Effusivity testing was completed at the end of February, and then just in time for COVID-19. So currently, for those of you that aren't aware of the West Coast of the United States, University of Oregon and other universities in the United States are not allowed to collect any human subject data during the COVID-19. So we are waiting to conduct the perception testing and to analyze the data. And we're hoping that we'll be able to be back on board in the summer to do that. But we really can't confirm that date at this point in time. So I'm going to go through, before I go through the perception test protocol, I'm going to talk a little bit about the materials and the results of the effusivity testing that was conducted by C-Therm. We generated a list of about 37 fabrics, and those fabrics were provided by the industry partners. And you'll see in this diagram that we have general material description and fiber content. The general material description is how the materials were defined by color. So you can see there's like different stripes of color. And you'll see that each color block actually is kind of a sport product end use. So some of the end use is base layer. So that would be like the top layer, the top rows. We have t-shirt weight, we have pant weight, we have jacket shells, we have basic like woven shirting for like hiking, and many other sort of kind of classifications. We wanted to see, really, did all t-shirt materials, for example, test similarly? And where did fiber play into the role of this? We also collected information around material construction and also finishes. And those are not provided here, just so that you can see the table in this presentation, but we do have that information if you'd like us to share it. So then once we got the data, we then had it ranked. So if you look at the top row, so sample number 10 was the warmest, and then sample 28 was the coolest. And what's really cool here is that you can see that the blocking of the different stripes of color are not necessarily always grouping together. So you can see that different materials, different construction of the same construction are ranking differently. So these are the values from the face of the fabric. And then the next table shows the values from the back of the fabric, again, ranking from warmest to coolest of the 37 fabrics. So the question we may have here is, is the front and the back different? And this diagram, or the slide here, shows you that they are different. So like Aria said, in the sports industry, it's really important what side of the fabric you may use, because some fabrics are actually used on the back will be used for the face, and vice versa for the end use. And also in the sports industry, we're always thinking about next to skin touch. And we're also always thinking about what's the retail presence of the material when it is touching the potential consumer's hand. So really looking at both those values are really important in the sports industry. I'm going to go through the perception test methodology, and I think what's really important here is that to just say again is that the method was developed with the industry partners and really being mindful of existing methodologies they may have used in the past. And also, we have not conducted the data from this methodology yet. We plan to do that once we're reopened after COVID. So the perception test methodology, and I'd also like to add that I have a graduate student that will be running this testing with me. Her name is Emily Karolidis, so we're really pleased that one of our students can help with this project. The initial 37 samples, as you remember, the ones that Aria tested, were narrowed down to 15 for perception testing. And the way that we did that is the samples were selected according to the effusivity values, material characteristics, and sport apparel application. So we wanted to make sure that the 15 materials that were represented were not all like t-shirt fabrics, that there was a really good mix of different applications. The values were like clearly different, and that we looked at different sorts of finishes and construction of those materials to have like a really nice array. So we have the 37 samples that are narrowed down to 15, and then we numbered the 15 samples. So they're numbered according to their effusivity values. So sample 1 in this slide here represents the lowest effusivity value, where 15 represents the highest. From there, I'm going to talk a little bit about the human subject involvement. So the involvement of the human subject will include 3 visits to our lab. The first visit, the subject will look at effusivity samples 1 through 7, and they will conduct a perception ranking of those samples. At the next visit, they will look at the effusivity samples 8 through 15, and they will perception test rank those samples 8 through 15. And then in the third visit, we are going to revisit the perception rank samples 4 to 10 in order to refine the perception rank samples of 4 through 10. And what this really allows us to do is to ultimately see, does effusivity testing, does it line up to what people think? We are using what's called a fingertip rationale, and we're using this for a couple reasons. So the fingertip and the palm, through previous research, have been identified as the most thermosensitive regions of the hand. For this study, we have chosen the fingertips over the palm because previous studies have found them to be better to differentiate between everyday materials. And we have several academic journal articles that we've referenced for that rationale. So what I'm going to do with you guys now is really take you through the perception test method and show you what that looks like. This will be done through kind of these slides animating with the 7 samples. So depending on if the subject is coming at the first visit or the second visit, they will have 7 to 8 samples at a time to be tested. Each sample was cut to an 8.5 by 11 inch piece, and it's backed with cardstock as an environmental control. We didn't want to have any sort of conductivity of like a metal table or any sort of surface to interface with the perception. We also made the sample big enough so that the subject's hand couldn't touch the table. And the table we have underneath the cardstock of the sample is actually wood, so has low conductivity value. So Participants' hands will also be cleansed and thermal neutralized with room temperature regulated wipes. If you've ever had small children at home and had like a baby wipe warmer, we have one of those that we're using. And also, we will blindfold the participants so they're unable to see the test subjects or test samples. And then the participants will be instructed on how to touch the fabric samples using their fingertips of their dominant hand to touch or tap the fabric for under 5 seconds. So we really want, like, what is your initial feeling of the sample with your fingertips of the dominant hand? And we're using the dominant hand because that is the hand that people are using to, touch and interface with objects in everyday life. So here's the demo. So at each visit, the participant will be provided with samples, and they're going to receive them at 2 at a time. So they're going to have 2 samples, and remember, they're going to be blindfolded. So those samples will be placed right in front of them. And we're going to start with samples 1 and 2 in this example. And they're going to be asked, of these 2 samples, which one feels the coolest, or do they feel the same? And then the subject would tap them, and in this case, they said the sample 2 feels cooler. So in this case, sample 1 is currently perceived as the warmest sample, and we're going to place that up at the top of our table, and we're going to call that the warmest, and then we're going to introduce sample 3. So as the same question that was before, of these 2 samples, which one feels the coolest, or do they feel the same? In this demo, the subject says sample 3 feels cooler. So since sample 2 was already identified as cooler to sample 1, the perception rank remains 1 and 2. We introduce sample 4, and we ask the same question of these 2 samples, which one feels the coolest, or do they feel the same? And this time the subject says sample 3 feels cooler. And so sample 3 is temporarily diverted in order to assess sample 4 against the current rank. So we introduce 2 because we need to understand how 2 relates to 4. We ask the same question of these 2 samples, which one feels the coolest, or do they feel the same? Sample 2 feels cooler. So sample 2 is temporarily diverted in order to assess sample 4 against sample 1. And then we ask the same question, which one feels coolest, or do they feel the same? And the answer is sample 4 feels cooler. So that then allows us to reorganize the rating from 1, 4, and 2. And now we're ready to assess samples 3 and 5. So we ask the question, which one feels coolest, or do they feel the same? And this time they feel the same. So what we do in this case, we move 5 and we temporarily divert it to assess 3 against 6. So we look at sample 3 versus 6. We ask the question. This time sample 6 feels cooler. We place 3 up next to 2. And then we have to understand 5. So of these 2 samples, which one feels coolest, or do they feel the same? Sample 5 feels cooler. So then 6 goes up next to 3. And then we look at sample 5 versus 7. Which one of these feels coolest, or do they feel the same? Sample 5 feels cooler. 5 goes to the coolest in this rank of the 7 materials. But now we need to figure out what's happening with 7. So then with 7, we compare it to 6. We ask the question, and in this case, sample 6 feels cooler. So we move 6 next to 5. And then now 3 must be compared to 7. So we bring 3 into 7, and we ask the question, which one feels coolest, or do they feel the same? And in this case, sample 7 feels cooler. So then we're able to complete the sorting of those 7 fabrics, and that's the result from the demo. This process would be repeated for the fabric backs, and this process would also be repeated for the second and third visits with assigned samples. So what I didn't mention here is once we collect that data, we will then be looking at how it relates to the effusivity data. We're also collecting some other data that we will also consider in the mix. So we're looking at weight of fabric, thickness of fabric, and seeing what the relationships are there with those materials. And then also, I think what's important to note is that, in this first project, we're just looking at a wide array of sports materials. So we have everything from t-shirts and base layers and pants and shirts and jackets. But future project opportunities could include by just looking at materials for base layers only or materials for shorts only. Other projects could include materials with defined percentage of stretch. So in this study, it's assumed that the material is fitting next to the body with there's no stretch. It's just, draping right next to the body without any pulling or compression. So an additional study could be made where you're actually fixing materials to a hoop and you're defining a percentage of stretch to represent compressive fit or a tight fit. We're looking at materials in dry conditions, but there's an opportunity in the future to look at wetted materials to represent the effect of rain or sweat on perception. And then also materials with one fiber type with different yarn, size, construction, and finishes. So lately, there's been a lot of development with cotton, for example. So, what if you just looked at a whole, array of cotton materials with different yarn, size, construction, and finishes? What would those metrics and values be? And then, of course, there's other things that you may be thinking that could be also useful to test and evaluate through these methods. And with that, I'm going to thank you, and I'm going to pass this back to Adam.
Thank you very, very much, Susan. That's a great overview. And we'll move quickly. I'm going to just wrap up with a few slides, but then we'll move this to a Q&A session. So I know there's been some great comments coming in throughout the presentation that I'd love to get your perspective on and help us address. So let me just share the slide. Okay, so we just had a couple of quick points we wanted to wrap up, and then we'll stop the recording and we'll open this up for a Q&A session. So the first point is just if you're looking for labs to help you with testing your materials, these are the third-party test labs that we're aware of offering our instrument for that as a test service, D7984. So in the US, we have PMIC labs on the West Coast. There's Axle Products, which offers contract testing services. They do a lot of work in polymers, but are branching out more into textiles. The group CTT up here in Canada and Quebec has some really impressive broader based research skills around textiles. They're a group that we've worked with quite a bit in the past and are very strong. There's also Bureau Veritas, which offers testing both in the US and in China. TAL is a division of C-Therm Technologies, so that's our own contract testing facility. And then in Asia, there's, in addition to Bureau Veritas, there's the Taiwanese Textile Research Institute, SGS, Intertech, are all offering this as a test service. So understanding that there may be other locations that are closer to you, more convenient for you to work with. These are the ones that we're aware of, and we're always happy to add to this list if there's others that you're aware of that are offering this as a test service. I want to put a quick plug in for our webinar next week. It's going to be on bio-based materials, mostly building materials. That's going to be Thursday, May 7th at 1 p.m. Eastern. We'll be featuring application work from recent publications. Sarah Ackerman, Arya's colleague, will be joining me for that presentation. So if you're interested, just enter that in the chat box, or I see Stuart's already listed the link there. You can register directly there. So at this point, I want to thank you very much for joining with us today, or if you're reviewing the recording, thank you for taking the time with us. I want to thank Susan in particular for putting this together. It's a really great working with Susan's group. If you're looking for a partner on the academic side to assist you with your research projects, I would highly recommend working with the University of Oregon. I've been really impressed and I'm really excited to continue pursuing this. And we've talked about some of the future opportunities. We'd love to get more industry participation in there. From my perspective, we're happy to help fund this, but C-Therm is bringing domain expertise in thermal characterization. This works best when we really get industry participating as well from the textile side and bring that expertise together, and that consensus building exercise that happens when we all put our efforts in the same direction. So thank you again, Susan, wonderful job. And I also want to thank Arya Hakimian, who supported the work from our side. Did a great job running the tests, coordinating with the University of Oregon, and has provided a really great summary of that here today. Okay, so we're going to open this up for the Q&A session. At this point, I will stop the recording, but stay on the line if you would like to participate in the Q&A.